In this video, we will set up the goals for a network vault mesh. In part 1 of the network vault exercise, we created the base mesh out of line network. In part 2, we continue with the base mesh. You may use your definition from part 1, or open the Grasshopper file provided in the resource folder to follow along. Let's begin building the definition. As the starting step for part 2, we need the base mesh, the trimmed surface, and the original line network. The first goal to set up is the anchor goal. To identify the anchor points, deconstruct the trimmed surface to extract the naked edges. Out of these naked edges, we must isolate these edges and find the naked vertices of the mesh that coincide with these edges. Use the endpoints component to extract the endpoints of the original curves into a point container. Also, extract the midpoints of these lines using curve middle component, and plug that into a different point container. Now we use the closest point component to identify the indices of the edge curves. Connect the isolated endpoints list into the point parameter. Graft, and simplify the input to ensure we find the closest point for every endpoint. Connect the midpoints list into the cloud input. The output from the closest point component is the closest points, their index and distance. We can use the CP index output, and extract the corresponding lines from the list of naked edges. Collect these lines into a line component. Next, we need to identify the naked vertices that coincide with these lines. Extract the naked vertices from the base mesh. Use the pull point component to pull the naked vertices to each line. Connect the naked vertices to the point input of the pull point component. And connect the list of edge lines into the geometry input of the pull point component. The logic applied here is that the point coinciding with the lines will be 0 distance away from the lines. Use a smaller than mathematical operator. Pass the distance values into first number, and a small number like 0.01 as the second number. Use the output from the operator to dispatch the list of naked vertices. List A is a selective list of edge points, or the anchor points for our anchor goal. Now that we have the anchor points, we need to find the target for these points. We start by making the circles. Use midpoint component to extract the midpoint of the selected edge lines. For radius, we will divide the length of these edge lines by 2. Connect these two inputs into circle component, and we get the initial geometry of our target curve. Use curve-curve intersection to extract the intersection points between anchor curves and circles. Connect anchor curves into curve A and circles into curve B. Out of the three outputs, param B is the list of parameters that identifies the intersection points for every circle. The list contains 8 branches, 1 for each circle, and 2 items in each branch. Shatter the circles using these parameters as input. Since the parameters are branched, remember to graph the curve input. The resulting output is 2 semicircular curves for each circle. Out of these, we need to identify the curve that is away from the initial line network. We can pick a point on the curve, and check whether it falls within the trimmed surface. Curves that are towards the initial line network will always have a point within the trimmed surface. The same isn't true for the curves pointing away from the surface, except for the endpoints. So, choose any point on the curve other than the endpoints. We will do that with the point on curve component. The 0 on this is the start point, and 1 is the end point, as you see on the screen. Set this slider to 0.07. Use B-rep's closest point with the surface is B-reps, and the point on curve is point. Out of the three outputs, we need to focus on the distance output. Use the sort list to sort the distances in ascending order, and the list of curves is additional values A. This reorganizes the list of curves where the first item is the curve intersecting with the surface, and the second item is the curve pointing away from the surface. Use list item and index 1 to isolate the target curves. Now that we have the target curve, we need to divide each curve according to the number of anchor points. Take the list length of anchor points, subtract it by 1, and use the number as division count. This gives the list of target points. At this stage, if we try to visualize the order of anchor and target points using line 2 points, we realize that the points are not in correct order. Out of the 2-point lists, target points are listed in the order following the curve. The anchor points list is jumbled up. To sort the anchor list, use the anchor curves as guide curves. Before doing that, ensure that these guide curves and the target curves are aligned in the same direction. Use the start point of both target and anchor curves, and check the distance between them. If the distance is non-zero, the curves are not aligned. Use the Boolean statement to dispatch the anchor list. Flip all curves from list B, and merge the two lists. Now use these aligned anchor lines as guides to sort the anchor points. Try making lines between the new list of anchor and target points to confirm the order. And it should be sorted now. Use these points with the anchor goal. For the other goals, we use show and edge lengths. Connect the base mesh into these two goals. For the load goal, we use all mesh vertices and apply a force vector in the positive z direction. Let's merge the goals and connect him to the solver. Enable and reset the solver. If the simulated mesh elongates beyond the desired size, try reducing the load vector to pull it back. Use list item to extract the first index from solver output, which is the simulation mesh. The simulated mesh is anchored at the target mesh as expected, and the mesh converges into a network of vaults. The naked edges and adjoining faces are skewed in proportion, giving an undesirable fold at the top. This is subjective as per personal preference. We will even it out using an additional length line component. By adding additional spring force to the naked edges, we are trying to shorten the edges, thereby shortening the archways. This should help in elongating the edge faces along the shorter dimension, and help improve the proportions. Use Mesh Edges component to extract the naked edges, and connect him to the line input of length line component. Set the length value at 0.1 times the length of each line segment. Use curve length to extract the length of line segments, and multiply the list of lengths with 0.1. Merge this goal with the rest. Also, set the strength value to 10. By doing this, we are increasing the effectiveness of the spring force in this simulation. Reset the solver. We can see the form has smoothened out towards the edges, and the edge faces have squarish proportions. Now that we have the complete definition set up, including part 1 and 2, change the initial line network, add more intersecting lines, increase the number of lines. The definition will revise the vaulted mesh accordingly. Just replace the input curve with the new set of lines works and reset the solver. Try building this definition, and explore different forms arising from it. If you'd like to use the form for architectural visualization, you may use Weaverbird's Mesh Thicken function to give it some thickness. In the next video, we will learn how to model complex minimal surfaces like Costa Minimal, and others in mesh form using Kangaroo simulation.